Welcome back. The objective of this video is to find an exponential function from its table of values. We'll explore some things about exponential growth and decay, and then we'll compare and contrast a linear function from an exponential function. Example 5 says, determine the formulas for the functions from the table of values below. Compute the average rate of change of y with respect to x and the ratio of consecutive outputs. So working with our parent function, y equals a times b to the x, or if you will, f of x equals a times b to the x in function notation. Let's take a look at our data. And one of the important points, as we know, in an exponential function is the point 0, 1. Well, that would mean anything to the 0 power is 1, and our a value would be 1. But in here, in this function, we have, when we input 0, we output 3. So we're going to have something to the effect of y equals 3 times b to the 0 power, because that's going to be 1. 1 times 3 is 3, and our output is 3. So we have just figured out that 0, 3, that y-intercept gives us an a value of 3. Then the next thing we can look at is our outputs, our y values. And that is going to tell us what our b is. And we can see here that our values seem to be doubling. And it's easy for me to see that, like 6 over 3, and then we're going from 6 to 12 is the same as 12 over 6. So when we kind of use a ratio here, we end up with our ratio is 2. Well, this is our b value. Our b value is the ratio of the consecutive outputs of y's. So then we know our function, pardon me, f of x equals 3 times 2 raised to the x power. Using the same information in g of x, now we know that g of x, we see our y's are 10 over 20 and 5 over 10. So we have a ratio of 1/2. So that ratio of 1/2 again tells us our b value. So we know our b is 1/2, and our a value comes from our y-intercept. That is 5. So we know our function is 5 times 1/2 raised to the x power. So a is 5. In example 6, we have a function of 3 times 2 to the x, and if a is greater than 0 and b is greater than 1, the function is increasing, and the base b is its growth factor. So we are growing by a factor of 2, so that means, in this case, we are doubling. So the graph of our function is going to look something like this. We have a growth function that's going to go through the point 0, 3, because anything to the 0 power is 1. So the 2 becomes 1, and we multiply that times 3. So as x approaches infinity, the limit, we're going to positive infinity, and x goes to negative infinity. Our y's go to 0. That's our horizontal asymptote. So our domain is all real numbers from negative infinity to infinity. Our range, our outputs, are going to be from 0 to positive infinity, and our horizontal asymptote is at y equals 0. In this particular function in g of x, now our ratio is 1/2. So if a is greater than 0 and b is less than 1, the function of f is decreasing. This is a decay model. So now our values are decaying by 1/2. This is like a half-life. So this is a decay factor. Now, our function is going to go the other way because it's decay, right? As x's gets really big, our outputs get smaller and smaller and smaller. This particular graph is going through 0, 5 because our coefficient here is 5. And the limit as x approaches positive infinity, we can see that's getting closer and closer to 0. Our product is decaying or decreasing. And the limit as x approaches negative infinity would be going to positive infinity. Our domain, again, is all real numbers. Our range, again, we won't have any y's that are at 0 or below. And our asymptote is still at y equals 0. In example 7, we have a word problem. Big Tech Industries has 25 locations and is expanding by 10 new locations each year. The company growth can be represented by b of x equals 25 plus 10x. So that guy, Big Tech, is linear because we have 10 to the first. So that particular formula for those guys is going to be b of 0 will equal 10 times 0 plus 25. While Central Computing Inc. has 25 locations and they expand by increasing their total locations by 40% each year. The growth can be represented by c of x equals 25 times 1 plus 0.04x, or c of x equals 25 times 1.04 raised to the x power. So when x is 0, so c of 0 equals 25, and b of 0 also equals 25. So these guys are both starting at the same place. But now you'll see the difference between a linear increase and an exponential increase, especially when our exponential is greater than 1. This is going to end up going up faster. So let's take a look at the stats. So I took the liberty of substituting x in for Big Tech Industries for each year. X is 1, 2, 3, and 4. And we see that those are increasing linearly by 10 per year. So 25 to 35 to 45 to 55 to 65. Whereas the exponential growth, we're starting at 25, and after 1 year, they're at 35, a 40% increase. But then it's a 40% on top of 40%, it's 49, and then 68.6 and 96.04. So these differences are growing at a faster rate. So thus exponential growth. We're asked to graph and compare the two. So I'm going to put on my x-axis, I'll label that. That's our years on the x-axis. And the y-axis is going to be our number of locations. Our output depends on our input. Our y's depends on our x's. Our locations depends on the year. So state the domain and range for b of x and c of x. When do both companies have the same number of locations? And what's the maximum number of locations for each company in 5 years? So this is, we're going to input x equals 5 into both equations. So let's go ahead and plot our data and take a look at our graphs. So I've plotted my points. The blue is our linear function, and our red scatter plot is our central computing, so our exponential growth. And when do the companies have the same number of locations? Well, they have the same number of locations at x equals 0 and x equals 1, where they're both 25 and 35. State the domain and range for b of x and c of x. So b of x has a domain from our x's start at 0, and they can go to infinity. And our range starts at 25, and that also can go to infinity. Where c of x, our domain, again goes from 0 to infinity, and our range also goes from 25 to infinity. So I've drawn my line for my linear function in blue, and then I can sketch my exponential function in red and answer the final question: what is the maximum number of locations for each company after 5 years? So b of x after 5 years, we could put it right into our equation. B of 5 equals 10 times 5 plus 25, or 75. And c of 5 equals 25 times 1.4 to the 5th equals about 134. So they're increasing at an increasing rate. So we've compared and contrasted linear and exponential functions, and you can see the difference there, how after a while they begin to separate. And we've also been able to find an exponential function from a table of values, and we've also graphed and compared them. So we've done that twice, but it's important to note that we have done a growth function, which rises as you read from left to right, and a decay function, which falls and heads towards 0 as you read from left to right. So it'll be important to note that distinction between exponential growth and exponential decay. And we'll get some more practice with this when I see you in class.